So today we're gonna talk about quantum harmonic oscillator, simple harmonic oscillator. And we started this discussion last time, but today we're gonna discuss more of this stuff. And let me actually start by this, whoops. Apparently that's not, oh yeah, let me start by this image. So when we talk about simple harmonic oscillator, all this mathematics, this is not just some random mathematics. People build gates and quantum devices that literally realize this. And this image is particularly interesting because it's from across the street in the physics department. So people do build, these are transmons, superconducting qubits. And the only way to model them is, based on my knowledge, is a simple harmonic oscillator. So the mathematics of this lecture literally describes this device and many other devices. But this is like the technological aspect of it. I just want to say that the light, like the bulbs, light bulbs, they're also full of harmonic oscillators, right? Quantum harmonic oscillators is ubiquitous. It's everywhere, right? Okay. This is particularly cool because it's large scale. It's like this is 3 micron scale. Yeah.
We don't have to get into it. The answer is complicated.
I would not be able to, but yeah.
Is that a qubit? Are the two states just like ground state and first excited state, or is it more?
Often, yeah. No, well, okay. So my understanding of this is super naive. There are people who work with an Alex Moss group who can give you a better answer. But basically, it's often systems that come in nature are often like infinite dimensional. And what you do is you design a system which sort of like excites you from one state to state 1 to state 2. And they go back and forth. That's like our model, usually, right? But sometimes it happens that the system is genuinely infinite dimensional and you can't take that limit, or actually you might not be interested in taking that limit. For example, in quantum optics. In quantum optics, we often talk about a system that's like, we're working a limit where it's actually infinite dimensional. But yeah. What we're going to describe today, by the way, simple harmonic oscillator is the basis of quantum optics. It's the basis of quantum field theory. It's the basis of anything that, pretty much anything that high energy theorists know. All right. Any questions before we start? I'm going to start as usual by review. Yeah, I'm recording. Good. I'll try to actually do a calculation today if you have time. So review of lecture 12. Let me stand over here. In lecture 12, we talked about a whole bunch of things, but one important thing that I want to remind you guys of is this Hamiltonian. This is perhaps like one of the most important Hamiltonians in quantum mechanics at this level. So what does it look like? It looks like a classical Hamiltonian of a particle propagating in some potential V of x. And we said that this form of Hamiltonian is easy. It's easy to guess what the quantum form of it would be. So we just put hats on all these guys. That we just promote x and p to operators, right? And it's easy because it's unambiguous. We don't have to decide order. We don't have xp multiplying each other, in which case you would have to decide the order. Then we found the operator equation, which looks literally like the classical equations of motion, right? F equal ma. I keep saying F equal ma. Hopefully that's obvious. But as an operator equation, right? As an operator equation. So in quantum mechanics, it looks like, it might be deceiving that the operators satisfy an equation that looks like F equal ma. Because as we will see, the consequent quantum mechanics is still very, very weird, as we talked about, right? But so what does this mean? Well, you could use it to calculate all sorts of things, but in particular, it implies what's called the Ehrenfest theorem, if I'm pronouncing this guy's name properly. And it's just simply the statement that if you take the expectation value of the left-hand side and the right-hand side, right, then what you obtain is that the expectation value of x evolves as a function of time, as you would expect from a classical evolution. So the expectation value of the position operator in the Heisenberg picture hopefully it's clear why we're saying Heisenberg picture, because operators evolve as a function of time. X is time dependent. Otherwise, this equation is nonsensical. Follows the classical equations of motion. So at this point, you should immediately see one main advantage of the Heisenberg picture. One of the key advantages is that it helps you compare nicely with classical physics. In classical physics, what we often do is Heisenberg picture, right? We describe this. We could do either. But every time you write F equal ma, or you're talking about the position or momentum of a particle as a function of time, you are in the Heisenberg picture. All right. But just to mention one weird aspect of quantumness of this equation, just make the simplest, pick the simplest case possible. V of x equals 0, a free particle, non-relativistic free particle propagating, just moving around. By the way, when I say propagating, is that a sensible word to you guys? It just moves around. But in quantum mechanics, because we're dealing with wave functions, the word propagates is more commonly used. Well, there's a terminology called propagator, blah blah blah. Does anyone know what the propagator is? We're gonna go over this later. Propagator is the amplitude, the transition amplitude for the particle to go from point X to point Y. There's a transition amplitude. Right. Okay. So I'll not go on tangents. So what we saw was that even when V of x is 0, so the particle is free, at times t equals 0, x is commute, p is commute, but x and p don't commute. But even x at time 0 and x at time t do not commute. As we calculated this, and we found this minus h bar t over m. One dramatic consequence of this is that we have uncertainty in position grow in time, right? So this is in tangible physics terms, wave functions expand. Why does that happen? It has to do with the fact that we're talking about, sorry, let me, a little correction. Spatial, like wave function in space expands when your Hamiltonian is diagonal in the p basis, right? So when your Hamiltonian is p squared over 2m, of course an eigenket of p will not expand, right? Because it's stationary. But the expansion of the wave functions come from the fact that the Hamiltonian is, for free particles, naturally written as p squared, whereas we're looking at the x basis and they don't commute. There was this question. Okay. By the way, just for those of you guys who are curious about this, there is one very, very dramatic thing. I'm going on tangent, sorry. About compare classical physics and quantum mechanics. Classical physics shows chaos. Quantum mechanics, for a very long time, people didn't know how to make sense of chaos. It turned out, this was like within my lifetime. It turned out, like, I was a grad student, that the approach, one simple approach is just to take the left-hand side of this thing, xi t, xi 0. It's an operator, square it. This has like been a hot topic of research. People measure the square of this, and it's a measure of quantum chaos. So a lot, like I told you, that there is a lot of stuff that we do in physics that might sound fancy, but a lot of it comes down to this simple solution. All right, enough tangents. So the Hamiltonian that we're going to be talking about is going to be a simple harmonic oscillator. We said that this Hamiltonian is literally, the classical case of this is like a string, a mass attached to a spring, right? That's actually, does anyone know why this appears so much in nature? Like, what is the simplest reason for that? Two atoms, right, act like a spring. If you push them together, they repel. If you pull them apart, they also want to come back. So they have equilibrium distance. So in some approximation, which is for those of you guys who are a little bit familiar with this, like equilibrium expansion around equilibrium, you can model the interaction of any two atoms as a spring attaching them. And this is what it is, right? So this is the classical Hamiltonian for a spring attached to a mass. P squared over 2m plus half m omega squared x squared. The trick we use to solve this, there are many ways to do this, but I absolutely recommend, I can't stress this enough, A and A dagger, lowering, raising operators are perhaps the nicest way to think about this. What you do is the following. You first take out an H bar, and then try to write this as a positive operator plus half, right? What is this? I just packaged, remember the idea was to, this looks like P squared times something plus X squared times something. So in the phase space, it looks like some sort of oval shaped thing. I don't have chalk. That is going to be interesting. All right, I'm going to do it here. So in the phase space, this looks like something like this, right? Depending on the mass and frequency. We just normalize things differently, rescale X and P so that this looks like a R squared or something, Z squared, and view it as a complex variable. And this is how we write it, right? A dagger, plus half H bar omega. So this plus half is honestly really an afterthought. If you just stare at this equation a priori, you haven't solved it, you can't tell. You have to subtract a half from it, like separate the half. But this is something that like people solve this equation, figure it out. This is a smart trick. Does anyone know why that half is subtracted? I hinted at this last time. Because what we wrote down is H bar omega. H bar omega has dimension of what? Energy. So H bar omega is just dimensional analysis. I've taken H bar omega out. What multiplies it is a number. Hamiltonian of a physical system is expected to have a minimum energy state, which means that that state will have some value for this operator that multiply H bar omega, which is a number, which is the smallest possible number, right? It turns out that number in this example is half. So if you subtract that, what sits next to it, N starts from 0 as the ground state and goes up. It's a positive operator, right? That's the trick. The number operator satisfies these nice commutation relations. Well, first of all, it commutes with the Hamiltonian trivially in a sense, and that's why we can use the eigenstates of the number operator to label eigenstates of Hamiltonians because they're simultaneously diagonalizable. They're compatible operators, right? So the eigenstates of the number operator, we call them ket n. And this is a self-adjoint operator, Hermitian operator. So its eigenvalues are real, but on top of it, I'm telling you, they're positive. Okay. All right. So from just based on the fact that these two guys commute, it means that if you take the ket n and act with a Hamiltonian on it, you're going to get H bar omega n plus half n. This is the energy of the eigen ket n. Is this part clear? I want to make sure every step of this is clear. Now, one interesting, the motivation behind doing this definition is that when you do define things like this, the ket n, then when you act with A on n, it still is an eigenket of Hamiltonian, as you can see from the commutation relations. When you act with A dagger, it's still an eigenket of the Hamiltonian. A dagger. So just a if I want to zoom out, what we are doing is that we're defining some algebraic relations, set of operators that generate all the eigenkets of the Hamiltonian. That's what we're doing. But these guys are not normalized properly. They are eigenkets. Is it clear that they are against any questions? I did this very quickly last time. Just use the commutation relations, right? But you have to, if you want to turn them into an orthonormal basis, you have to normalize them. So this is an orthogonal basis. They provide an orthogonal basis. I haven't proven to you that this is a basis for the Hilbert space, but take my word for it. I have to normalize them. So how do I normalize them? Well, let's take a ket n. What's the norm of this? I'm going to calculate the norm and divide the ket by square root of the norm. Right? That was our trick. I don't have chalk, but the trick was if you had some ket psi, if you wanted to normalize it, you would do this. You would send psi to 1 over square root psi, psi, psi. Now this is normalized. Unit norm. That's what I'm doing. All right, so what is the norm of a ket n? That's just a dagger a sandwich between n. This is a number operator. This is an eigenket of it. So the answer is n. You take the square root of it. Oh, sorry, I did not take the square root. So this means that a acting on n is just square root n ket n minus 1. Is this, are these two lines of algebra clear? All right. Similarly, you repeat this for a dagger. Now you end up with a dagger. Every time you're dealing with these expressions, you either end up with a dagger a, in which case this number operator, you apply it and you know what the eigenvalues are, or it comes out the wrong order, a dagger. You use a commutation relation, so you write it as the number operator plus the commutator. What is a commutator? 1. Right? So the answer comes out as n plus 1. You take a square root. A dagger of n is square root of n plus 1 ket n plus 1. Sanity check. Once you do this, calculate this. What is it? A square root, this guy is square root n minus 1, right? That's just a line above it. Then I act with a dagger. That's square root n, because this is n plus 1 of n minus 1. N minus 1 plus 1 is n, right? N. Sanity check, right? It all works out. Now you know that n is positive, right? But you knew that, right? Because we wrote it as a positive operator. Good? All right. Now, if the advantage of this method is that if there is a ket which has eigenvalue 0 for for n, that deserves to be called the ground state, right? Is that clear? Because all the other eigenkets will have larger eigenvalues. Why? Does anyone want to explain why? A bit louder. Exactly. N is positive. N is positive. All right. So that state we're going to call the vacuum or ground state. And it's the state that in this war-driven terminology is killed by A. So very good. That's what the state is. Let me see. Whoops. Yeah. So this is a ground state. What's this energy? What's the ground state energy? H bar omega n plus half. N is 0, so it's H bar omega over 2. This is the ground state energy of any harmonic oscillator, a single harmonic oscillator. How do I find the excited states? Well, I act with a dagger repetitively on it, right? If I act with a dagger once, I get ket 1. Is ket 1 defined this way normalized properly? What's the, yeah. What is the norm of ket 1 as I've defined? No, what's the norm of ket 1 as I've defined? Sorry, I'm just so tempted to write on the board, but I'm going to do it here. So let's calculate the norm of 1. What is that? That is 0, A dagger, 0. Everybody's with me? Right? This is 0 commutator of A dagger, 0 plus 0, A dagger, A, 0. What is the first term? Sorry? 1. Because the commutator of A and A dagger is 1, and the overlap of 0 and 0 is 1. Right? Okay, that's 1. What's the second term? 0. There we go. So it's properly normalized. Let's go to ket 2. I'll put square root 2 in there in anticipation of the fact that I have to properly normalize it. Well, it's a little exercise for you guys to check that once you put the square root 2 over there, it's properly normalized. But that's just a one-liner, right? Like all I need to do is I have to put 2 here, right? Now these become 1, 1, 1, 1, and 1, 1. What's the first term now? Still 1. What's the second term? 1. So now it becomes 2. I have to divide by square root 2 to have a normalized state. Good. So that's just one line of algebra. So this way, using a dagger, I generate all the eigenkets of the Hamiltonian. Again, the big caveat is that I did not prove to you these are all that there is. But any questions about this? So you could check explicitly that the n ket n is an energy eigenstate with energy h bar omega n plus half, and it's a dagger to power of n divided by square root of n factorial. So that those factors of square root 2, those factors that you have to put in there are square root n factorial. Good? Now let's calculate. Any questions? Yeah. Say it again.
Are these states
They're all eigenvectors of the Hamiltonian and the number operator, yes.
how do you know that? If there's something else,
Oh,
that is not generated by.
that's what I was saying. So I did not show. I showed to you that these are actually eigenstates of the Hamiltonian, but I haven't proven to you that there exists no other ones, right? But take my words for it. You could prove that. I just don't want to go on that detour, right? That's just like a little bit of basically differential equations, but I didn't want to do that. But yeah, that's a very important. In general, oh no, okay, let me not go on tangents again. All right, very good. So what are these a dagger operators? So this ket n, you should remember, think of as make a comparison with what when we were talking about the qubit, the Stern-Gerlach, remember? What was it? We had some SZ operator, and what were the eigenvalues? So we were talking about these two vectors. We call this plus, we call this minus. The expectation value of ST in this guy was h bar over 2, this was minus h bar over 2. In comparison, in this case, we have a Hamiltonian. We should be thinking of as an infinite vector, right? One-sided infinite, like it's just, I start with 1, 0, 0, 0, 0 all the way. This I'm gonna call ket 0. What's the expectation value of Hamiltonian here is h bar omega over 2, right? The next one is going to be 1, 0, 0, 0, 0 infinitely. This is 1. The expectation value of Hamiltonian here is 3h bar over 2, omega over 2, right? And so on and so forth. So if you used to call this a qubit, you can call this, like think of it as an infinite dimensional version. A qubit had d levels, a d level system. This is a limit where d is infinite. Also, having said that, now you would not be surprised that in some other notation, people, instead of writing ket plus and minus, they ket plus, ket 0 and ket 1. Oh, sorry, the other way around. How do I want to define? Okay, whatever. They use ket 0 and 1 for these guys, depending on their notation. Right? All right. So have these matrices in mind. These are like half infinite matrices, right? What is when we calculate? So now it's time to ask, what are these A dagger operators in this basis, right? To do that, I have to look at the matrix elements. So the bracket of A prime on the left and A on the right. Well, that's easy to calculate. A acting on n gives you square root n, ket n. And the bracket of n prime and n is just delta of n prime. Oh, sorry. Ket n minus 1. And the bracket of n prime and n is the Kronecker delta of n prime and n minus 1. Similarly, that's the A dagger. What does this mean as a matrix? Can you imagine it? So what is the n? N is n delta of n prime, right? What is this number operator as a matrix in its eigenbasis? As a diagonal matrix, right? I don't have chalk. Is that possible? There should be some like random piece of chalk somewhere. All right. Well, let me write here. Let me just write here. I don't want to go on a scavenger hunt. Chalk. So the n operator looks like this. Whoops. It's diagonal. What do I put on the 0, 0 element? 1, 1 element, like the vacuum element. 0. I've removed h bar omega. Remember, n is just the eigenkets are just positive integers. Then 1, then 2, then 3, Good. So that's in the number operator. It's a diagonal matrix, but it's an infinite matrix, half infinite. What is A? Yeah. I mean this. So positive numbers, positive integers are half infinite. You start from 0, 1, 2, 3, and you increase, you go to infinity. Real integers, real and negative, positive and negative are not. They're infinite from both sides. Like, I'm sorry, I said half infinite. The terminology that we use sometimes is inaccurate. Is it clear? Okay. So now you have this formula. What does this formula tell you about the operator A? How do I write it? Tell me how to write A. So, yes. What's that operator called? Sorry, no. First, that's the correct answer. What are the diagonal elements of operator A? 0. What are the elements above the diagonal? 0 as well. Right? Actually, wait, sorry. Is it the other way around? So this would be A acting on a ket. Wait a second. So I have to have this. I have to have 1 or n. So here's how I know it, right? N A 0 has to be 0. Good. What does that mean? No. In terms of the matrix element. Yeah, I think the first column has to be 0. Because, right? Because take the, like A is yeah. This N is acting on the left like this, right? So it's 0, 0, 0. There's a 1 here, right? Yeah. I'm confusing myself. Yeah, that's correct. That's correct. That's correct. So, yeah. So here, it's a, sorry. Look at this formula. What if I put n equals 0? If I put n equals 0, arbitrary n prime has to be 0, right? What does that mean? That means that, so the nth and arbitrary n prime is here, right? And the first column has to be 0. So it's 0 below the diagonal. Yeah, that's right. Then it's just above the diagonal. Here, I start with square root 1, square root 2, and so on and so forth. This tridiagonal. It's upper triangle and tridiagonal. Similarly, a dagger is like, has the thing 1 line below. It's important that the diagonals are 0. We'll see that the physical implication of that. Can anyone tell me right away what is the physical implication of that? What was the operator x? Schematically, it was a plus a dagger, right? If I calculate the diagonal elements of a plus a dagger, what is it? 0, because these are both have zeros on the diagonal. That means that the expectation value of the x operator in an arbitrary eigenket of energy is 0. Good. All right. Actually, that's my next line. So let's calculate the x operator and the matrix elements of x operator. Here they are, right? I trust you guys can plug in a bunch of numbers, but the point here is that this is also now this is tridiagonal. The diagonal element is 0. One line above and below, one diagonal above and below the diagonal are non-zero, and everything else is, right? Similarly for the p operator. Good. So here I'm going to make you pause and ask for questions because my next point is going to be somewhat tricky. Are there any questions here? The reason I'm stressing on matrices, this is not really fundamental in a sense, but I remember when I was learning quantum mechanics, thinking of matrices helped. Maybe that doesn't help you. Do you guys know what Gram-Schmidt is? It's a method for diagonalizing matrices. Okay. So I haven't taught Gram-Schmidt, so I'll not make a comment. But the fact that this those of you guys who know Gram-Schmidt, this should like be suspicious. That's just one line below the diagonal, one above the diagonal. It's not suspicious. This is by design. All right. So if there are no other questions, I'm just gonna calculate. What's my next point? Calculate the wave function for the eigenket n in the position eigenbasis. Right? What did I just describe? I described the bracket of x prime and n. Wave function for eigenket of the number operator or the Hamiltonian, the nth energy eigenstate. It's typical. We typically order energy eigenstates, right? Increasing energy. By the way, what's wrong with the system that doesn't have lowest energy physically? Well, negative energy is not necessarily a problem because it could always shift energy, make the low. The problem is the lowest. The fact they should have a lowest energy. That's one way of putting it. But what's an example of a system that has no lower energy state, just classically? What's an example of a system classically that has a lower energy? Give me an example of Hamiltonian. Come on, guys. This is a Hamiltonian. Harmonic oscillator, exactly. This. So this. V of x, this is V of x is this, right? This has the lowest energy, classical and quantum mechanics. How do I turn it into a system that doesn't have lowest energy? Multiply by minus sign. Flip it around. Right? Now, why is this good physically and an inverted harmonic oscillator bad physically? What's bad about an inverted harmonic oscillator? Like the motion of a particle in a harmonic oscillator oscillates. What's the physics of an inverted harmonic oscillator? The term of physics uses instability. Things roll in a random direction forever. Right? That's instability. So remember this, a physical system that doesn't have a lowest energy state, classically or quantum mechanically, is unstable. Good? That's the issue. But it is true, like the things just roll and then, well, this has dramatic consequences. We study systems with instabilities, and yeah, it's a beautiful topic in physics, but not for this level of quantum mechanics. All right, so back to Earth. Let's compute the wave function, this wave function. The way I'm gonna do it is, of course, we invented these tricks of A and A dagger, so we're gonna use them. What is this expression, x prime a 0? That's just 0. Why? Because a kills the ket 0. Right? Okay, very good. Let's write what a is. A is x plus ip over m omega, some coefficient outside of it, but I don't care about the coefficient because it's equal to 0. I dropped the coefficient. So as an operator, I can insert this inside this, and I should get 0. Good. Now, x acting on x prime just is x prime, so it comes out. IPM omega acting on x prime is, how do I calculate the action of IP over m omega over x prime? It has to act on the left, right? So first I have to take the Hermitian conjugate of it. What's the Hermitian conjugate of IP over m omega? Minus IP over omega. All right. We said that P is I ddx prime. So I just plug it in. And it's convenient to define this guy, x naught squared, as h bar over m omega. So this is like x naught up to an h bar. Right? So all I've done is just, I've derived this equation. Now, what is this? This is a differential equation for the ground state wave function. Thank you so much. Thank you. Yeah, so now, oh, this is wonderful. So now, what was my notation? This was x prime, x0 is 0. What is the name of it? If I want to shorten your language, this is the ground state wave function. This is a differential equation for the ground state wave function. And x naught, I told you, is h bar over, no, what was it? H, yeah, that's how you find it. Good. So how to solve this equation, differential equation? It's just a first order differential equation. You know how to solve it. Right? So I'll not elaborate any further. Here's the answer. You don't believe me? Plug it in. Now you see why I defined this x naught. Because this x naught sits as a normalization. What is this wave function? Can you describe it to me? What is it? It's just Gaussian, centered around which point? 0. Right? What's the width of it? What parameter controls the width of this Gaussian? X naught. Good. So if here is a picture I can draw. This is the x direction. I'm gonna draw. By the way, the wave function came out to be real. Didn't have to be, but it came out to be real. So I can draw it on a just like. So I'm gonna draw psi 0 of x prime. What does it look like? It looks like this. It's a. Whoops, sorry. What am I drawing? That's the potential. It looks like this. It's a Gaussian. Right? This is the width of it. X naught is controlling the width. But importantly, you see immediately centered around 0. Now, x naught controls the width, which means that if you have a harmonic oscillator, if you make your harmonic oscillator, your particle mass heavier, increase the mass, how does this wave function change? X naught, if m becomes large, x naught becomes smaller, so it becomes pointier. Right? Now, there is a very interesting lesson to be learned. Okay, maybe I should not. But let me just say very quickly. When m is very, very large, this is very, very pointy. Right? And just remember this in your head. Systems that have that have large mass in h bar, appropriate h bar units, are more classic. This is an energy eigenbasis. Eigenstate, momentum eigenstate, and we're plotting it in the position basis. So the fact that the two operators don't commute is the origin of this width. But when I make the mass very, very large, it's just some lesson for you guys to think about. Classical limit has to do with h bar and also masses. Why is that? Okay. Awesome. All right. So this is a wave function. Are there any questions about the ground state wave function? It's a Gaussian with this wave. The number is weird. Pi to the power of 1 over 4 square root x naught is just normalization. Yeah.
You apply at the same time evolution of these states.
My next point is that. Yeah, we'll get there hopefully. Now, how do I calculate the first energy eigenstate? Well, I just have to put a dagger in the middle, but I know what a dagger is, in terms of x and p operators. What is it? X minus ip over m omega up to an overall constant that I'm going to keep track of. And you're going to work out your homework. So you just do that, keeping track of everything. This is the equation you end up with. Right? Now, the position wave function of the first energy eigenstate, you wrote as a differential equation, differential operator acting on the vacuum ground state. This method relates the vacuums, the higher energy states, to the vacuum wave function. But then you just calculate the vacuum wave function up here. So you just take the derivatives and find what this guy is. And you repeat this. You just do this for the nth energy eigenket. And here's the expression. It's some sort of differential operator to the power of n, some sort of complicated differential operator acting on this exponential. Now, if you remember from your undergraduate quantum mechanics, you might have seen it in an ugly form. The energy eigenkets of the harmonic oscillator, if you actually do these derivatives, you're going to get a mess. Those are called Hermite polynomials. They're mathematically some stuff, some functions that are somewhat ugly, but this is the origin of it. They're basically some differential operator applied to Gaussians. They're all coming from Gaussians. So what do these wave functions look like? This is how they look like. I drew for you the ground state wave function. I drew for you this guy, right? This is a Gaussian. Well, this picture is drawing it wider, right? Then the first energy eigenket, when you calculate it, it comes out as, by the way, oh, very good point. What is the imaginary part of this wave function? 0. It's all real. That's why I can plot all of them here. You should be a little bit alarmed that they're all real. There's something very interesting going on. But that's why I can plot this wave function, or I can plot the square of it, which is a probability, right? Now, what I'm plotting here is I'm plotting the wave function or the square. The wave function, because it goes negative, right? Good. So what you see is that psi 1 changes sign to the left and the right. Psi 2 has this funny property. If I take the square of this, what picture do I find? Just take the square root of the square of these wave functions. What does it look like? So I get this thing. What's my next one? I get this thing. What's my next one? Let me erase it so that I don't make a mess. I get these patterns. Have you seen these patterns before? Interference patterns. There will be, actually, I'm lying here because there should be nodes, right? Because the wave function hits 0 at some distance away, right? So these should really, well, in experiments, you see bumps like this. There's a reason for that, but here, see it's like this. This is just interference patterns. So what we learned is that this was a particle, a quantum particle. It behaves like wave. However, okay. No more random comments. Any questions? Any thoughts? No? All right. So just one so let's say it takes psi 4 of x. What is that in our in the notation of the book? This is what it is, right? It came out to be real. What happens if I evolve this wave function with time? Is it gonna is it possible that it remains real? What is evolution in time? I have to stick in here e to the power of I minus I over h bar. This is an energy eigenkit. How does an energy eigenkit evolve under time evolution? Picks up a phase. And phase have real and imaginary parts, right? So it will not remain real. As a matter of fact, you instantly can tell why is it real here. Well, maybe you cannot tell, but all right, is it good? Now let's calculate expectation value of operators in this. The expectation value of x is 0 in the ground state. As a matter of fact, you saw pictorially that the expectation value of x is 0 in all these ket ends. Right? Is that clear? Because is that clear? No? Why do I say that the expectation value of x is 0 everywhere for all these eigenkets? Because the wave function is symmetric under flipping x to minus x, right? So the wave function has identical support on the negative side of the real axis and the positive side of the real axis. Therefore, it must be 0. The expectation value of x must be 0. But you know how to calculate it, right? the way you calculate is using A and A dagger, right? The diagonal elements of that operator are just 0. Turns out that the vacuum has 0 momentum. What is x squared and what are x squared and p squared? You just calculate them. I trust you can calculate them. It's just a couple of lines of algebra. X squared comes out to be half x naught squared. That actually tells you that this is the width. P squared comes out to be h bar omega m over 2. Right? P squared over 2m is the Hamiltonian. So that's related, Hamiltonian is, okay, sorry, this is an important point. So when we calculate x squared and p squared, we found these expressions, right? Now, what was Hamiltonian? Hamiltonian was p squared over 2m, omega m over 2x squared. So I can ask which part of the energy, so Hamiltonian has a kinetic term and a potential term. How much of the energy of the ground state is due to the kinetic term? How much of it is due to the potential term? That's what I'm asking. It turns out that in the ground state, they're very equal. Half of it is kinetic, half of it is potential. You should be a little bit bothered by the fact that the particle is just sitting at the center, but it has a kinetic, it's picking a kinetic piece to its contribution to its energy. The expectation value of P is 0. The expectation value of P squared is not 0. This is quantum mechanics for you. Right? That's mind-boggling. But hopefully you know how to do the algebra, you know how to calculate. Don't ask me if I have intuition about this. No, I do not, but I know how to calculate. All right, so let's calculate the uncertainty relations. We calculate the uncertainty at delta x squared, delta p squared. You find h squared over 4. H bar squared over 4. That saturates the uncertainty principle. So the ground state saturates the uncertainty principle. States that saturate the uncertainty principle are the closest kets we have to classical physics. We said that if you talk density matrices, we can have literally classical states, right? Diagonal states. But as far as the ket goes, these guys are the closest. So in anticipation for a comment at the end of this lecture, let me just give you an alternative definition for the set of states that saturate uncertainty relations. They have the least position momentum uncertainty relation. In simple harmonic oscillator have a name. Does anyone know the name? They're called coherent states. I'll get to this at the end, but I cannot stress this. Coherent states are so important. You cannot get away without understanding. They're extremely important. That's actually where our intuition comes from. All right, so vacuum state is a coherent state. Now let's calculate delta x squared, delta p squared in an energy eigenket, n. It comes out, I'm just giving you the answer, you could calculate this. It comes out as n plus half squared h bar. Oh, that's right. Is the n energy eigenket a coherent state? No, it has larger than h bar squared over 4 uncertainty. So it's not. Only the vacuum state is. So in our search, that immediately tells you that in our search for coherent states at the end of this lecture, we're going to be talking about states that are time dependent. So this is my next point. I'm going to make a pause because we're going to be talking about time development, time evolution. I don't know why the book calls it time development. Time evolution of the oscillator. Any questions? Yeah.
This is maybe So we're building up sort of layers of abstraction, but then we still usually define some sort of commutation relationship with creation and annihilation. Sort of, do those commutation relations always track back to the relations for X and T?
Very good. So it's in a sense, let me tell you the high level answer. We start with an operator. We started with an operator X. We define a canonical conjugate of it through translation. Right? They are called canonical conjugates because they satisfy this nice relation of X hat P hat as IH1. All I needed to define creation and annihilation operator was that. However, creation and annihilation operator are useful because of the operator A dagger A, number operator. The number operator looks like a simple harmonic oscillator, p squared over 2m plus half omega squared x squared. So any setup, you have this. So every time you give me an observable, I can define the analog of an NA dagger, right? Because I define the conjugate momentum, there are conjugate pairs, blah, 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 all of that goes through. But whether it's useful or not depends on your Hamiltonian. When the Hamiltonian is this p squared plus x squared, it is useful. And the systems that are x squared plus p squared are Gaussian systems, they're free. So for physicists, these are free systems. I'm sorry, the term might be confusing at this level. I should not say free, Gaussian. For high energy theories, these are free, but there's a potential for sure. Any other questions? All right. So in the Heisenberg picture, we're going to now calculate the time evolution of operators in this system. I'm going to stick to the Heisenberg picture because things are nicer, but I want you to remember that you could do this in Schrodinger picture, right? Or if you want some mix and match, you could do some interaction picture. Not here actually, but yeah, you could do Schrodinger or Heisenberg. Heisenberg is nicer because it closely relates to equations of motion, right? Operators, observables evolve as a function of time. So now, because I'm in the Heisenberg picture, X, P, and A as operators are time dependent. And here are my equations of motion. You recall how I derived them, right? How did I derive them? It's just Heisenberg equation. What? There's one subtlety here. When I derived the equations of motion, evolution equation in the Heisenberg picture, what was it? It was ddt, the LLT, but observable was, I think, minus, plus, I think, anyway, pi. It was this. But this was an observable, self-adjoint operator. So I can apply it to X, I know the evolution of X and the evolution of P. So I add the two terms and get the evolution of A, right? Because A was written as a convex, X plus I something P. All right. If you calculate d dt of A, what you find is this expression, you massage it, you learn that d dt of A is minus I omega A. Similarly, d dt of A dagger is I omega A dagger. Remember the picture I was advocating for you guys to have in mind? I said A and A dagger, the philosophy was to normalize things on the phase space, P and X, and view it as a complex plane, and then so that A becomes something like this, a vector like this. Now, the time dependence of these two operators, if you integrate these two equations, it just tells you that the annihilation operator evolves by phase e to the power of minus I omega t. The creation operator evolves with a phase e to the power of I omega t. That means that this guy is a rotor, it starts spinning around, right? It just goes around. And its dagger goes in the opposite direction. as operator, these are just cartoons for you to remember, right? These are not, hopefully it's clear. These are analogies. I'm making a lot of classical analogies. But you know the algebra, you know how to do calculation. Calculations are not by staring at this picture, they're done by calculations, right? This is just a post-thought interpretation thing. All right, so now that you know how A and A dagger evolve, you know how x of t evolves. X evolves as a function of t because you know how to write down. Actually, why is that? So what is x of t? Hopefully this is obvious. But what is x of t? As e to I h t over h bar x0 e to minus I h t over h bar. Why can I integrate it and write it this way? Because the Hamiltonian time independent, right? I just integrated the Heisenberg equation right away. Good. Let's plug in for x. I forget what it was, but just I'm going to schematically write it. It looks like this, right? Some numbers here. So, oh, sorry, A and A dagger. I actually think, yeah, it's something like this. So this means that I know that because I know the time evolution of A and A dagger, I know the time evolution of X. Similarly for P, right? So I derive these guys. These are just some phases going in the opposite direction. One of them goes this way, the other one goes the other way, right? So I know the expressions. What it looks like is two terms. One of them, yeah, okay, sorry, maybe there are two phases, right? E to the power of I omega t, the other one e to minus I omega t with different coefficients. That smells like cosines and sines, right? You just do the algebra, it's a one-liner, and this is your answer. X as a function of time is x naught cosine omega t plus p naught over n omega sine omega t. This also matches the picture I was drawing, right? This thing going around and the phase space. It also looks, yeah, okay. Everyone is okay with this? Oh, wow, I'm really behind. Similarly, you do this for P of t. P of t also oscillates in this nice expression. Good. I will not get to coherent states today, but because I want to do a good job of this Baker-Haas account. Good. Are there any questions? I'm gonna pause because I'm not gonna have time to go through coherent states. That's for the next lecture, but I want to explain this properly. But before doing that, are there any questions about the solutions so far? Yeah.
So the free particle, there was like kind of smearing with time. But in this case, it stays like pretty localized.
What happens here?
It just sort of bounces back like a pendulum.
Hopefully we'll get to that. And now maybe today we will not get there. So for now, you're seeing one thing. That picture pendulum thing is not literally true. Why? Does anyone know why? Look at the solution. Okay, sorry. Let's look at the solution. This is an operator equation. Pick your favorite eigenstate. What's your favorite eigenstate? Mine is ket n. A generic one. All right, so let's calculate this. It's cosine omega t n x0 n plus sine omega t over m omega ket n p0 n. What is it? Oops. So what's this term? It's 0. What's the next term? 0. So this equation, again, quantum mechanics, operator equation could be deceiving. The operator looks like it's oscillating, but the energy eigenkets are not doing that. Yeah, that is the thing, the danger of these phase space pictures I was drawing.
That's saying that the expected position is staying. That's what that is saying.
Exactly. Exactly. You're up to something. You're absolutely up to something. What is so? Let's calculate this guy. You're asking what is it? What is this guy? Right? So this is del x squared, del p squared. This is the uncertainty, right? You're asking how does this evolve as a function of time, right? Well, maybe you can calculate that and tell me. But I have a comment to make about that the next time. All right, any other questions? Now, so this is the object of interest. We just calculated it using A dagger, but I'm gonna tell you it's a mathematical identity. It's extremely useful. It's extremely useful. It's just, I cannot stress that enough. It's another method of solving this equation. In general, what is the structure? Every time you have an operator, a matrix, sandwiched with two operators like this, where this and this is -1, the other one. So it's basically something for this relation, if you wish. A to the power of x, e to minus x. Like some matrices. All that matters is that if you set this guy to identity, this is just the whole thing, they cancel. Right? In quantum mechanics, this kind of structure comes up all the time, right? Why? Because that's the Schrodinger evolution, Heisenberg evolution for operator observables when your Hamiltonian is time independent. So there's a mathematical method to calculate this. It's called the Baker-Campbell-Hausdorff, BCH. I'm not going to prove it. Actually, don't know how to prove it. It's pretty involved. I've learned at some point, I've forgotten, like most of the things I learned. But this is the identity to remember. There is, I assure you, there's physics in these terms that look so ugly. So let me explain it. It is an expansion as a function of lambda. Well, think of it as a series expansion, Taylor expansion. The 0th order term is A. That's reasonable because if it said 0 and 0 here, you just get A back. The first order term is I lambda commutator of G and A. Can you see how that comes about? Let me do it. E to the power of I G lambda A, e to minus I G lambda. So this has as an exponential has a C Taylor expansion. It looks like this: 1 plus I G lambda plus order lambda squared. And A, this guy similarly, A1 minus I G lambda plus order lambda squared. These two guys give me A, that's my 0th order term. What's my next order term? Plus I lambda GA minus AG. I've written as a problem, plus order lambda. Good. You go to higher orders, it might look ugly, but it has the structure, the terminology for this is nested commutator. The next order term is the commutator GA, again commutator G. The next order term is GA, commutator G again. The nth order term is I lambda to power of n over n factorial, this nested commutator. Good? Sorry? Was this zeros you said?
Yeah, that's a 0.
No, this is order.
Oh, okay.
Yeah. So we're that's just the notation. Something that's lambda squared or smaller. When lambda is small, this is lambda squared or smaller. Yeah, if there's something about my notation, please ask. Okay. All right. So take what we're gonna do is we're gonna calculate x naught time evolution of x, right? This is using the formula we just had. So what is this? This is x naught plus it over h bar. That's this term, right? Commutator of h and x. I know from equations of motion for simple harmonic oscillator, that's minus I h bar over m p naught, p of 0. Then this is the next order term. What do I need to calculate? I need to calculate the commutator of h, commutator h and x. Commutator of h and x was proportional to p. So I actually have to calculate commutator of h and p. It comes out as x. The next order term is h and x again, it's p. Next order term, h and p again, x. So they alternate. All the odd nested commutators end up being proportional to p. All the even ones end up being proportional to x. I'll include a homework problem for this. But nicely, you could resum them and you obtain x naught cosine omega t plus 1 over m omega p0 sine omega t. These expansion coefficients are the series expansions of cosine and sine. This is in agreement with what we found before. This is actually what I was saying. There was a question about this, that these even though as operator equation, they might look like they match your intuition, but when you put them inside the expectation value of states, it might confuse you, right? So in this case, we see that the time evolution of xt and n is 0, expectation value. So what is a classical state? So this I'm just going to prep for the next lecture. A classical state will oscillate back and forth. There's a state that sits. So classically, there is a ground, only the ground state is static, time independent, right? Everything else, you're just pushing this up this and it rolls back and forth because there's no friction, it just oscillates, right? The equations, as operator equations, show oscillatory behavior, but we are not seeing it in ket ends. All of these ket ends, their expectation value is just stationary, time independent, right? So what are the states that mimic this behavior? Classical behavior. They are called coherent states. They are exactly the same states I said minimize the uncertainty relation. Vacuum is also a coherent state because it behaves as you expect classically, expectation value of it. And we also saw that it minimizes the uncertainty relation. Are there any questions? It's the end of this lecture. Next time I'll have to go over coherent states. It's a beautiful, beautiful story. But any questions about today's lecture? I absolutely, yeah. There was.
Yeah, it was like feedback not available, but I didn't see it.
Oh, one more thing. Okay, thanks so much. I'll check. Yeah, one more thing. I think one of the homeworks I posted, I said it had one problem from Sakurai or something. I'm cutting everything off of Sakurai, so there won't be much more from Sakurai. But there was one problem that was two problems from Sakurai, and I said the edition this time as opposed to last time. So I said it's the revised edition, third edition. Turns out it's not the newest edition. So I meant what I said. The revised edition is 1990. It's called the revised edition 1994.
Yeah.
Somebody pointed out that there was an edition that came out later. Because like they gave me a copy of the book and in physics department, I had no idea. It's what you would expect. Just type yes. I think they all are red.
No, they're all
What?
Yeah, they're all blue. The revised edition's only blue. There's one with a cat, there's one that's just blue. The cat one is.
All right, how about this? If you
Yeah.
They circle a bunch
So
of-
that's.
I thought they were
The
the
revised
same.
edition is
Oh.
basically the second edition.
Oh, I'm sorry. Okay, so I'll confuse you guys. So for now, because it's my mistake, no matter which edition if you have already solved it, it's okay. But from now on, if I do have a problem from one of Sakurai edition, I just take a photo of it. You put it there. Okay?
That's a good idea.
Yeah, phones are made for that. All right. Any last questions? If not, thank you so much.